Hello, my name is Darren Thomas and I'm the Director of Educational Research Techniques. In this video, we're going to take a look at confidence intervals, but this time we're going to take a look at confidence intervals in the context of proportions. And so we'll try to explain this in the next slide or two. So we have our example here at the top, but before I get to that, when you're talking about confidence intervals, normally they're associated with continuous variables, such as the mean. You know, that's the most commonly used time that confidence intervals is used. But anything else that can be measured in a continuous manner, so correlation, even R squared can have confidence intervals, etc. But when you're dealing with confidence intervals for proportions, you're dealing now with categorical variables. So success versus the total number of possible observations or samples, if you will. So the proportion of boys in a population, the proportion of people who pass an exam, whatever. When you have these categoricals, pass or fail, male or female, etc., it's not a continuous variable. So therefore, the way you calculate the actual interval is slightly different in that particular context. So before I get any more complex, I think it's better to look at an example here. So as you can see here, it says 70 students out of 100 passed a quiz. Find the 95% confidence interval of the proportion who passed. So again, notice here we have two things that can happen. Students can pass or they can fail. That's it. There's no other options around here. This is different from calculating the mean, where it could be 1, 1.01, 1.02, etc. It's not continuous. It's pass or fail. So therefore, we're looking for something slightly different. Now, again, we're still looking kind of sort of, it's not exactly like this, but we're still kind of looking for something where the tails are cut off on both sides, and we want to try to find this little distance in here of the proportion, okay, but instead of the mean, if you will. But it's still an interval because we're trying to calculate that distance where we exclude the tails. That's what we're trying to do here if you're familiar with, a distribution. And it's not exactly like this, but this is just to make it, to simplify it for you, if you will. Now, there are many, many things that we have to piece together first. First of all, let me go over here and change the color a little bit. We need to figure out what is our X, what is our N, what is our P hat, and what is our Q hat. That's what we're looking for. So our X is going to be the number of successes. In our context, that's going to be the number of people who passed. So that number is right here, 70. So we're going to go ahead and put that in here. So it looks like 70 people passed. Now our N is our total sample size. So in this context, it's 100. Now, for the P of hat, it's slightly different. P of hat is going to be X over N, which in our case is going to be 70 over 100, which can be reduced down to a decimal of 0.7. That is our P hat. The number of successes when you break them down to like an actual proportion, if you will. Now, Q hat is slightly different. This is so important, I'm going to change the color again. Q hat is going to be 1 minus whatever P hat was. Now, in our situation, P hat was 0.7. So 1 minus 0.7 equals 0.3. So this is all the information that we need to continue our analysis. We need this right here, this 0.3. We need this 0.7, and then we also need, or I think actually that's it. That's all we need for right now. So this is all the information that we need that we're going to plug into our equation in the next slide here. So here is the actual equation for calculating the confidence interval for proportions. So you have P hat minus your z-score, whatever z cutoff you pick. So in our situation, it's going to be 1.96. I'm assuming you're already familiar with how that is calculated or how that comes about. Multiplied by the square root of P hat times Q hat over N. And then after that, we have our actual proportion right here. our population proportion, if you will. And then we have p hat again, this time, oops, excuse me, p hat again, plus our z divided by 2, all that over p hat and q, sorry, I'm running out of space here, divided by n. That's what's going on. So this is the actual expression or the equation that we're going to use. Now we simply plug in our numbers. So our p hat, if you remember from the previous slide, whoops, our p hat was right here, 0.7. So I'm going to plug that in. So 0.7 minus, now our z is going to be 1.96. That is when you convert the alpha, which is 0.05 in this situation. Again, I'm assuming you know what I'm talking about. 0.05 is the 5% that we're excluding for the tails. So when you divide that by 2, you get 0.025. And when you convert that, you get a z-score of 1.96. That's what we're doing here. Again, I've explained this before. So 1.96, this is our cutoff. So anything that is about 2 standard deviations below is extreme. We're removing that. Okay, that's what we're doing. And then we're going to multiply this all by, probably put this in parentheses, 0.7, that's our success, times 0.3, that's our failures, our Q hat, if you will. All this divided by 100. And then we have our P hat. And then I'm going to write this below because I'm running out of space. And then we have 0.7 again, this time plus 1.96. All this multiplied. Oh, that the whole thing should be, this should be the whole thing, sorry. 0.7 times 0.3, all this over 100. And then we're going to close that out. So that's our equation right there. Now we're going to keep this simple. I'm not going to multiply this out all in front of you, but here's what it looks like when you do this. So what you end up with, when you deal with this information all right here, when you calculate all this, you're going to get the number 0.89. So the final expression is going to be like this: 0.7 minus 0.089. And then we have this, then we have our population proportion, and then we have 0.70, I guess you could say, plus 0.089. That's what you get. And so when you simplify this, you get a very simple answer of 0.61 p to 0.78. So this is our answer right here. So what we're saying is that our 95% confidence interval will have a value that is between 0.61, 61% to 78%. We can expect the population proportion to be somewhere within this range, which is very reasonable. And this is how you address this. And so having this knowledge, again, you're able to infer what is happening in the larger population, which is the primary purpose for calculating confidence intervals. So in this video, we covered a lot of complex information. We took a look at confidence intervals and how to deal with them. And so simply with confidence intervals for proportions, you're looking at how to calculate confidence intervals for categorical variables, pass, fail, male, female, etc. And so in this particular example, there are several things you need to know. You need to know your X, your sample. You need to know, observations, if you will, or success, however you want to call it. You need to know your sample size. Your P hat, as I mentioned previously, is going to be the number of successes over the number of failures. That's what it's going to be. All right? That's what it's going to be right here. And then also you have to know your Q hat, which is going to be, the time when you're unsuccessful, if you will. When you have all this information, you plug it into the equation. I know this is not the most beautiful equation, but it is here. And when you calculate it, you're able to get that actual range there. So we hope that this was practical and useful for you as you continue to address and to deal with statistical analysis. So my name is Darren Thomas. I'm the Director of Educational Research Techniques. Take care.